So in this second video on functional groups, I'm going to cover the alcohols. Here's an example of an alcohol. This is methanol, and this is the group we're interested in. That's the functional group. That's an oxygen, and that is a hydrogen. And so it is bonded to a carbon. So that really characterizes the alcohols. The functional group is this hydroxyl group, or OH, and it's considered as a branch or branches off a carbon chain. So oxygen is not going to be part of that chain. So there's a wide variety of different alcohols. Here's a second alcohol. So this with two carbons would be ethanol. So we'll get into the nomenclature. It's pretty straightforward though, as I think you'll see. Nomenclature, identified by an alcohol by the presence of a hydroxyl group, so that makes it an alcohol, not an alkane or alkene or anything like that. It becomes an alcohol. Parent molecule is named according to alkane nomenclature, except now we take the E of an alkane name and replace it with the suffix ol, ol. And so that is about it. If necessary, the position of a hydroxyl branch is indicated, and that's common now. And when you have multiple hydroxyl groups, they can be known as diols or triols, just number of OH groups. So if we look at our first example here, there's our identify. So this is an alcohol because of the presence of that hydroxyl group on a terminal carbon, or carbon 1. So we would number those carbons, and we'd have to indicate position of that hydroxyl group. So this is going to be, it's a 6 carbon, so it's hexane, so we make it hex-an 1 ol. So we've replaced the E with an ol, and we've indicated a number or a position with that number, which we would have to do. Isomers of hexan 1 ol, of course, then would be the simplest isomer, hexan 2 ol. We just move the OH group to carbon 2. Hexan 3 ol, and move it to carbon 3. So that's why we need the position. Here's a second example. So there's our hydroxyl group, OH, and it's not on carbon 1, not on terminal carbon. So we're going to number to minimize that. So there we go. So that is an OH group on carbon 4. We also have this methyl group on carbon 4, or sorry, carbon 2. So that's going to be 2-methyl. It's a 4 carbon molecule, so that's a butane 2 ol. So carbon 2 is where the hydroxyl group is. Now, one other way you sometimes see it, it's not nearly as common, but it can be done, is look at our hydroxyl group as a branch, and we call it a hydroxy branch. Hydroxy, not hydroxyl. And so you could also name that as 2-hydroxy 2-methyl butane. And so there you're just treating the OH as a hydroxy branch. Not nearly as common. At this stage you should be able to name that as an alcohol with the ending OL. To draw these then, again, the name tells it all, so pretty easy to get these sorted out. So that's a pentane. There's my 5 for a pentane. On carbon 2, I have an OH group, pentane 2 ol. And on carbon 3, I have an ethyl branch. And I would satisfy the bonding with additional hydrogens. And there's my drawing for 3-ethyl pentane 2 ol. Butane 2,3-diol. So again, the di is telling us there's 2 OH groups, and the numbers in front tell us where they are. So there's our butane, and there's a carbon 2, and there's a carbon 3 hydroxyl group. And that is a diol. Just notice one thing with multiple hydroxyl groups. So when you have a diol, a triol, you leave the E on there. You don't replace the E stays. And that's the only real difference there. Quite subtle, but it is a bit different. So just like the haloalkanes, alcohols can be classified, and just like the haloalkanes, it's based on the number of carbon atoms attached to the carbon that bonds the hydroxyl group. So once again, we look for the hydroxyl group and the carbon atom bonded to. So there's our hydroxyl group with the zinc bonded to the carbon, and this carbon is bonded to only one other carbon. So that is a primary alcohol. And that primary alcohol would be called, because it's a 5-carbon alcohol, pentan 1-ol. So that primary alcohol, pentan 1-ol. Now, we also have secondary, and so this is going to be an example of a secondary. Don't forget there's carbons present there in this stick diagram. They're not shown, but I'll just show them there. And once again, look for the functional group and the carbon. So the functional group is on carbon 3, and that carbon is bonded to 2 other carbons, so that's a secondary alcohol, and it would be called, so we have 1, 2, 3, 4, 5, 6 carbons, so that's a hexane 3-ol, because the OH group's bonded to carbon 3, so that's a secondary alcohol. Finally, obviously this is a tertiary alcohol. Hopefully you can see why. Here's my OH group with the carbon, and so that carbon bonded to 1, 2, 3 other carbons. So that's why it's a tertiary alcohol. And this tertiary alcohol would be known as 2-methyl propan 2-ol. So a tertiary alcohol. Easy to see why it's tertiary, because the numbering is the same for a branch and the position of the OH group. 2 and 2 tell you that's a tertiary alcohol. So finally, we have to consider polarity in alcohols, and just like haloalkanes, the hydroxyl group is polar. It's very polar. The delta N is about 1.4 for an OH bond. That's a large difference in electronegativity. So alcohols will always have this bond dipole, and hence will have a molecular dipole, or will be considered polar molecules. And so, again, to reiterate, polarity is going to help us describe certain physical properties and why they're different in different organic compounds. And so we can look at a comparison right now between ethane, C2H6, and ethanol, C2H5O. And so ethane, all of the bonding is nonpolar. Nonpolar carbon-carbon bonding, nonpolar carbon-hydrogen bonding. So that's a very low boiling point, minus 89 degrees Celsius. So ethane is in fact a gas under standard conditions because it vaporizes at such a low temperature. Ethanol, on the other hand, has this polar functional group, and the delta N there is going to, between the oxygen and the carbon, gives us a bond dipole, and therefore a fairly negative aspect to this molecule. So that negative aspect of the molecule is going to allow it to form electrostatic forces of attraction with positive aspects of another ethanol molecule. And that electrostatic force of attraction keeps the molecules there. You have to apply more energy to vaporize the molecules, and so hence the boiling point of ethanol is significantly higher, 78 degrees Celsius. So ethanol is a liquid at room temperature. So there you have the alcohols, characterized by the hydroxyl group, characterized by a large molecular dipole, and hence some interesting physical properties based on those dipoles. And that concludes this video.